Hey everyone, you are watching this video during our lecture on Tuesday, October 26th. And this is the second of two lessons on frames. And what I want to start out with is first to review our first lesson in frames that happened this past Thursday. So I'm going to change to my paper and I'm going to pin myself. Well, I guess it doesn't matter because there's nobody else on, so I don't have to pin you. All right, so the first thing we did on Thursday is we said, if we had a pin that had a reaction in the X and a reaction in the Y, and we found that the reaction in the X was 100 pounds and the reaction in the Y was 100 pounds, it's important to know that this pin, overall, the pin needs to withstand a total of 100 squared plus 100 squared force coming off at it, because the resultant of this force is going to be going up in this direction and it's going to be pulling on this pin. So even though we had a calculation of 100 pounds this way and 100 pounds up, the pin is really going to be subjected to 100 squared plus 100 squared under the radical, which I think is 141 squared. Let me just try. Squared times 2 equals under the radical. Yep, 141. So this pin really needs to withstand 141 pounds. So that was the first thing that we talked about on Thursday. The second thing I introduced on Thursday is something that's called two force members, three force members, etc. And the way we define whether a member is a two force or a three force, your question to yourself is, how many locations on the member are there forces? So if we have a member, a bar, that has, let's say a pin on the left and a roller on the right, there are only two locations where there are force reactions. And so this is called a two force member. If we have a bar, let's just say it's turning, and right here there is a pin, and then let's say there's an external load of 10 pounds here, and then there's a roller here, there are three locations on here where there are forces. So this would be considered a three force member. And the reason you may remember that this is important to know is because normally, let me go to the next page. So this is page 1. Page 2 is if I have a member that has a pin here and a pin here, we ordinarily, and let's say this is point A and this is point B, we would ordinarily say, oh, it's going to be an AX here and an AY here and a BX and a BY. But we learned last week in class, let me focus this better. We learned last week in class, when you do have a two force member, the loading in that member goes axially along the body. So if I redraw it now, and this is my point A, and this is my point B, because this is a two force member, the force that goes through the body is AB and AB. In this case, it's in compression. I could have drawn it the other way if I wanted. I could have drawn it away, which would be in tension. But I know that the total load goes right through this body. And what is really awesome about this is, instead of this drawing where I have four unknowns, because I recognized it's a two-force body, it gets converted to knowing two force members only have one force that goes through axially. I reduce this problem from a complicated problem of 4 unknowns to 1 unknown. Okay, that was the second thing that I did on Thursday. Okay, the next thing we did is we started looking at frame problems. And as I said on Thursday, you already know how to solve frame problems. So let's look at the frame the first problem we looked at, and let me put it clear. So it says, determine all the forces acting on member A, B, E. This is an E here. And so what we noticed is we had 3 members. And what we did first is we practiced doing free body diagrams. We drew a free body diagram of the whole structure, removing it from its pin supported A and roller at D. And then we took each member and we drew a free body diagram of each of these members. Now, as we just known, we know that when it's a two-force member, it's going to help us simplify the problem. So let's just take a look at these. This guy's a 3-force member because there's connection here, here, and here. This is a 3-force member because there are 2 connections and there's a force. And this is a 3-force member, connection, connection, and connection. So what we did from this problem is we took this problem and we drew all the free body diagrams, all the forces in the free body diagrams. And we realized that whenever we did that, if, for instance, for E, CEF, for CEF, if we drew E to the X to the left and EY down, wherever E connects, which is over here, to ABE, we knew that the E's, EX and EY, had to be equal and opposite. Because if I take this bar and take this bar and put them together, these forces would cancel because then it's considered an internal force. That's the same thing with the B here and the B here. When I connect these two, they become internal forces. And it's the same with the C here and the C here. When I connect them, they become internal forces. And when I look at the free body diagram of the whole structure, notice I am not drawing EXEY here. I'm not drawing BXBY here. I'm not drawing CXCY because those forces are all internal. But I am drawing the 150 Newton external support, force. I am drawing my normal at the roller at D, and I am drawing my AX and AY at the pin. So that was the next thing we did. Draw all the free body diagrams. Now, this problem asks us only to find the members, all the forces acting in a member A, B, E. So I'm going to approach this problem just like any statics problem where we have a given and a find and all that. But I'm going to rely on this free body diagram, these free body diagrams. So for this problem, the given was the sketch. And the find was determine all the forces acting on ABE. And if I look at ABE, I have AX, AY, BX, BY, and EX, EY. Okay. So let's think about this as a regular statics problem. In a regular statics problem, we would now do force, moment, table, right? First is given and find. Second is the table, magnitude and direction. And man, I have a hell of a lot of forces. Let's first put down AX, AY, BX, BY, EX, and EY. So far, nope, 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 nope. I'm going to just draw a line under here. 1, 2, 3, 4, 5, 6. So just from the ones they want us to find, we have 6 unknowns. And is this a two-dimensional problem or a three-dimensional? Two-dimensional. We have 6 unknowns. We need 6 equations, and it's a 2D body. So we need 2 bodies. And why is that? Is because this is a rigid body statics problem. And for a rigid body, we have some of the forces in the x equals 0, some of the forces in the y equals 0, some of the moments about some point in the 0. So every two-dimensional body, every two-dimensional rigid body, we have 3 equations. So if we have 6 unknowns and we need 6 equations, we need 2 bodies. And in these problems, in these rigid body frame problems, the best free body diagram to use first is the whole structure together. Okay, and we're going to come back to that in a minute. We do know, though, that this problem doesn't just have these 6 unknowns. Yeah, we have A, B, E, but there's also a CX, a CY. There's also an N. That's it, right? So in addition to the 6 they want us to find, there's also a CX and a CY and an N. And we don't know those values either, but we do know their directions. The problem is not asking us to find these, but it does introduce another 3 unknowns. And we don't know, in the process of trying to find these 6, we might actually need 1 more body. Okay, so they're asking us to find AX, AY, BX, BY, EX, EY, but there's also a CX and CY, and there's also an N. Okay, so we're going to keep in mind that this is all the problem wants us to find, these, but by doing so, we might introduce more unknowns. And if we do, we might actually have to have another body. Like I said, for the frame problems, the first free body diagram you want to do is of the whole structure. So I'm going to just redraw it. We have it drawn already. Let me just redraw it. And this is all 100, 100, 100, 100, and this one's 200. So let's bring it out a little bit more. I have my N here. I have my 150 newtons here. And I have AX and AY. So first step, given and find. Second step, table. Third step, free body diagram. Okay. What's the fourth step? Remember? The fourth step is always finding the components of all the forces and doing the checks. But in this problem, every single force is in the X or Y, so we don't need to solve for components. So the fourth part is to do my equilibrium equations. All right, so let's take a look at this. And again, we want to be efficient. We don't need to find the normal because it doesn't ask us to find the normal, but we do have to find AY and AX. Well, let's see. Can I use one equation and find one of these values? And the answer is yes. I could do sum of the forces in the X is AX plus 150 equals 0, and AX is equal to negative 150 newtons. What does that negative means? What does that negative mean? It really means that AX is going in the other direction. But we drew it this way. We got a negative. We're cool. Sum of the forces in the Y. Well, I don't want to do that equation because this is an unknown and this is an unknown. So how about I do sum of the moments about the point where N is, which is D. Sum of the moments about D. Well, I have 150 times 200, positive, negative, it's negative. And then I have AY times 300, and AY, that creates a negative moment. And then I have AX times 100 equals 0, and that creates a positive. So this 150 created a negative moment times the 200. See this 200 here? I have AY, it's a negative, times 300. Here's the 300. And then AX times this 100, and it's positive. And in the end, I know I have the values here, so I think I'm going to look them up. So I don't need to pull out my calculator. Let's just see if I do have them. Maybe I don't have them. I don't, so I'm going to pull out my calculator. Okay, so I have 200 times 150 equals negative. And what is AX? AX is a negative 150. I have to put the negative 150 in here because that's the direction that AX is in my drawing. I have to make sure that I put in the negative 150. So I have negative 150 times 200. I have negative, I need another. I have a negative 150 times 100, and I have equals 300 times AY. So I have a negative 150 times 200, and that's negative 30,000. And this is 15,000, and it's equal to 300 AY. So my AY turns out to be, hopefully I'm doing the math right, 150 times 200, 30,000 negative minus 15123, yes, divided by 300. It turns out to be a negative 150 newtons. Okay, so with one free body diagram, I was able to find both AX and AY. Okay, but I still have 4 more that I need to find, and I may actually come back to this free body diagram. But when doing frames, the best free body diagram to draw first is the whole structure. Okay, let's go back to all these free body diagrams. Let's see. I also need to find the B's, and I also need to find the E's. I am thinking I might like to use this free body diagram next. I'm going to use the free body diagram of CEF next, which has an EX this way and EY this way. Y. It has a CX this way. It has a CY that way. And it has a 150 Newton here. And let's see the distances. The distances are 100 and 100. Let me turn this so it's upright. Just to check, I have CX and CY. They're both drawn positive. EX and EY. Okay, so I need to find EX and EY. So is there one I could find? Yeah, if I did sum of the moments about C, these two would cancel, this would cancel too. So it would be EX times 100, and that's negative. And then actually it's positive, EX positive, and then 150 times 200, and that's negative, and that equals 0. So EX is 150 times 200 divided by 100. And this is going to be, this is brought to that's going to be a positive. So 150 times basically 2 is 300 newtons is equal to EX. So now I solved EX. I could find CX, but that's not one of the ones I need. If I found CX, I found EX. So let's go to another free body diagram. I still need to find, so let's say I have AX and I have EX, and I still need to find B. What about using free body diagram ABE? ABE free body diagram. I have EY, I have EX, I have BX, I have BY, I have AX, and I have AY. I know that AY is negative 150 newtons. I know AX is equal to negative 150 newtons. I know EX is 300 newtons. I still don't know these guys, and that's what I need to find. What if I did sum of the forces in the X? I have AX plus EX plus BX equal to 0. So BX is going to be equal to, let's just write the numbers because we don't want to mess up with the negatives. 150 plus 300 is equal to negative BX. I bought. So BX is going to be equal to negative 150 newtons. Let's just make sure. It's going to be 50. I keep BX here and I put EY. Yep, 150. Let me just try it another way just so I make sure that I don't mess up. BX is equal to negative AX minus EX. Negative AX is negative 150 minus EX, and EX is 300. That would be 150 minus 300. And yes, I got the same answer, so I checked it off. So now I have BX equal 2. So now that's all I'm left is finding BY. And have you just thought of where you might want to do that? If we did sum of the moments about point E, I know BX now, I have all these. I could find the moment that BY causes. So the moment, let's put the distances. And now this pencil is running out of ink, lead too. Let's make sure this one has some lead. This one's good. Okay, so if I do sum of the moments, this is 100, this is 100, and this is 100. Sum of the moments about E, BY times 100 negative AY times 100. AY times 100 is negative. BX times 100 positive. AX times 200 positive. Let me check again. So I'm looking at E. These two are not going to create a moment. BY is negative times 100. AY is negative times 100. BX is 100 positive. AX is 100 positive equals 0. So negative 100 BY minus 100 times AY. And what's AY? AY is negative 150 plus 100 times BX, which is negative 150, plus 200 times AX, which is 150, equals 0. So negative 100 BY is equal to this times this. Well, let's just keep it all. Don't move anything over yet. This is going to be a positive 15, 1, 2, 3. This is going to be a negative 15, 1, 2, 3. And this is going to be a negative 3. I'm going to have to calculate that. 200 times 150 equals 30,000. And it's negative equals 0. So this is a plus 15,000 minus a 15,000. So BY is equal to, bring this to the other side, 30,000 times a negative 100. It's going to be equal to negative 300 newtons BY. Boy, takes a long time to do frame problems, huh? So far, we looked at the whole frame, the whole structure, and we found AX and AY. So I'm just going to cross them off up here. I found AX and AY. Then I went to free body diagram CEF, and I found EX. I went to free body diagram ABE, and I found BX and BY. And the only thing left now is to find EY, and I could still do this on this free body diagram, right? So I could do sum of the forces in the Y equal EY plus BY plus AY equals 0. So EY plus, what's BY? BY is negative 300 plus AY is negative 150 equals 0. So EY is going to be equal to 450 newtons. Okay, let me number these pages. That was page 1 and 2. This we'll throw in as page 3. This was page 4. This is page 5, and this is page 6. So this is a frame problem. They were asking us to find all the reactions at the supports in member ABE. We started the problem. We did the given and find. We did our table for just those 6 unknowns, and we knew we needed at least 2 free body diagrams. But we also noticed that there are 3 other unknowns that may come into the problem, and we might need another body. Because we had started this problem by drawing all the free body diagrams, I was able to look at these and figure out, well, which one do I want to use first? And as I said before, in a frame problem, you always start with the free body diagram of the whole structure connected, removed from its main supports. And from that, we were able to get AX and AY. Then knowing that we had AX and AY, we looked at another place, this place, where we were able to find out what EX was by looking at the free body diagram of CEF. And I did some of the moments about C, I found out what EX was. And then I went to the free body diagram of really the member in question. So let me just point out what winds up in frame problems is it's always very important to do a free body diagram of the whole structure because it simplifies things, because all these reactions in the supports are all internal forces. And also for a frame problem, it's great to do a free body diagram of the member in question. Okay. All right. I'm gonna put the recording on pause for a moment. Okay. The second problem that we worked on last week that we're going to be looking at and completing is this problem in front of us. It says determine the horizontal and the vertical components of the forces of each pin. The suspended cylinder has a weight of 80 pounds. So we looked at this problem, and the first thing we did, because we learned about two force members, is we took a look at BE, and we saw that this is a 3-force member because there are pins here, there's a tension here, and there's a pin here. We also looked at this member, ABCF, and that's a 4-force member. And then we looked at CD and we saw that, oh shoot, this is a 2-force member, and it could have been replaced with just a bar here. So what do we know about, even though there are pin connections here, and we would ordinarily put a DX and a DY and a CX and a CY, we know that the load that the pin is carrying is in the axial direction, in the direction from C to D. So we took this problem and we drew all the free body diagrams of it. So for the whole structure, we had an EX and an EY here. We had the 80-pound weight here. All this is still intact. This is intact. This is intact. At A, we're removing it, and this is a roller. So we also know we have a normal here, right? And I don't know if I think we decided to call it AX instead of N, and that's why we put this in red. And then at D, when we ordinarily would put a force in the X and a force in the Y, which we did initially, and then we crossed it out because we knew that this force is going in the direction towards CD. So for this problem now, for this free body diagram of the whole structure, we have an EX and an EY. We have an N or an AX. We have a CD going from D to C, and then we have our 80 pounds. And the problem is asking us to find all the unknowns, every unknown. So boy, this is going to be a long problem. Remember, we also drew a free body diagram for EB. E, we had an EX and EY. For B, we had a BX and BY, and we had the 80-pound tension because this is a continuous cable. The weight here, 80 pounds, goes into this cable and comes up here. We also looked at the pulley, which had a pin in the middle, and that's point F. We drew a FX and a FY, and we have an 80 and 80 pounds. And then from A, B, C to F, we drew equal and opposite F. For CD, since here we drew it going, let's see if we're having it drawn from C to D. Here we drew it up D, we drew it from D to C, which means equal and opposite C to D. So then when we draw it here, we have to draw it up to the right. And then additionally, we had B, a BX and BY that had to be equal opposite of this. And then we have our A. So this is a long problem. So let's do our given and find first. So 1, given, they tell us that the weight is 80 pounds, and also given is the sketch. In terms of find, you have to find everything. So let's write down everything we need to find. We need to find EX, EY. Actually, let's just put them all on the table. C table. So we're going to make our table. Force, moment, magnitude, direction. And let's put them all down. So we have EX and EY. We have at A, there's a roller. Let's just call it AX. We have no DX, DY. We have a DC, and that's equal to CD. If you want to use both sets of variables, you just have to make sure that we know they're the same. We have a BX and a by. We have a cx and a cy. And we have an fx and an fy. Let's see if we have everything. Oh, we have the weight, which is equal to the tension, and that's 80 pounds. So we know that one. So let's see if we have everything. EX, EY, BX, BY, AX, which is really a normal. We have a DC that goes up to here. BX, BY, we have a FX, FY, and we have the T. So we have, these are all question marks, and this is all checking. So what the hell do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 unknowns. We need 10 equations. It's a 2D problem. We could get 3 equations from each one. So we're going to need 4 bodies. And what body did I say always start out with on a frame problem? Always start out with the whole structure. So let's draw the whole structure. This is E, this is A, this is D. Nope, this doesn't connect here. This is C. This is F. Here's a pulley with my weight going down. And here's my tension that's connecting right here. Remember, I always have to draw the X and Y axis. And I need to make sure I put all the distances on here. So this is 3 feet, 3 feet. This is 6 feet, this whole thing. So that means this is 3 feet, 3 feet, 3 feet, 3 feet. This is 4 feet. This is 4 feet. And the radius here is 1 foot. Up, and the pulley, actually, I have to draw it closer. The pulley hits here. £80, and this is 1 foot. Okay, so now, what are the reactions at the supports? Well, the reactions of the supports are, what reactions are on here? We have an EX and EY. And we have our AX. And at D, we know that it's going to go along this direction. And we drew it going up. So this is DC. So now, if we do sum of the forces in the X, we're going to have 1, 2, 3 unknowns. If we do sum of the forces in the Y, we're going to have 1, 2 unknowns. If we do sum of the moments about this point, we're going to have this is an unknown and this is an unknown. If we do sum of the moments about this point, we're going to have this an unknown and this is an unknown. So basically, with this free body diagram, there are no equations that I could see of that are going to give us only one unknown in equation. And we do have a force that has components, right? So we should find those, do those component forces first. So, and look, it goes over 6 and it goes up 4. So that's 6, 4. Right, up 4, 6. So DC is equal to DC times 6i plus 4j over radical 6 squared plus 4 squared. And the units that we're looking at is going to be in pounds. So what does that turn out to be? Six squared, 36 plus 16 under the radical. Let's just try it again. 16 plus 36 under the radical. So it turns out to be this whole thing right here is 52. So 6 divided by 52, let's move this up, is 0. DC times 0.1154i plus 4 divided by 52 equals 0.0769j pounds. And let's just do a check. I don't think that's right. 6 divided by 52 equals 4 divided by 52 equals, let's see. It's not coming out right. 6 squared plus 16, 36 plus 16 equals 52. It's under the radical, that's why. See, I'm really glad I did a check. If you were live with me, somebody would have corrected me already. .8321 squared plus and 52 4. The numbers just seem too small. 0.5547 squared plus 0.8321 squared. Yep, equals 1. Okay, awesome. And they should both be positive, so I'm good. All right, so step 1 was given and find. Step 2 was the table. Step 3, well, we have one free body diagram, and we found step 4, we're finding some of the components. But now we're going to have to do a lot of free body diagrams now, which we've already drawn. So let's take a look at some of these free body diagrams. I'm looking at this pulley one. I can see that that looks like it's going to be pretty easy to find the values. So I'm going to look at pulley free body diagram, and some of the forces in the X are minus 80 minus Fx equals 0, Fx equals negative 80 pounds. Some of the forces in the Y equal negative 80 minus Fy equals 0. Fy turns out to be negative 80 pounds. So far, I only got the F's. Okay, so now where do we want to go? Well, if we have the F's, there's going to be many. If we do I have a feeling. Let's try this one. Free body diagram, BE. And you could see it right here. I have a feeling that we're not going to have efficient solutions, and we're just going to have to come through and do a bunch of equations. So let's see, if we did some of the moments about B, X, Y, and EY would be in it. If I did some of the moments, so I'm just going to go for it and say some of the forces in the X, EX plus BX plus 80 equals 0. Some of the forces in the Y equals EY plus BY equals 0. This turns into be BX plus EX equals negative 80. So here's one equation. Here's another equation. And remember, I could get 3 equations from each free body diagram. So I'm going to go ahead and actually find a moment equation too. I'm going to do some of the moments about E. Some of the moments about E is going to be by times 3 positive, bx times 4. Let me just check that distance. 4. And that's going to be positive, plus 80 times, I believe it's, so take a look at this quickly. The radius is 1. If this is 1, that means this distance here is 3. So this distance is, let's not put 3 here and 1 here. So 80 times 3, and it's going to be positive. So I'm doing some of the moments about E. I got by positive, bx positive. This equals 0. 3by plus 4bx equals negative 240. That's equation 3. So do you see why I'm starting to just go through and just crank out equations? Because I am not, there are so many unknown variables in here that I am not able to find some of the unknowns by just doing one equations. So in the end, I'm going to have a huge matrix to solve. Let's just go back and look. We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 unknowns total. I already found fx and fy. So now I only need 8 equations. I am actually going to use the main equation. I'm going to use the free body diagram of the whole structure again to find more equations. So I'm going to do sum of the forces in the x. Remember, for one free body diagram, you could have at most 3 equations. If you write a 4th equation for one free body diagram, it is only going to be a combination, an algebraic expression of these equations. You can only get 3 equations from a 2D body. So sum of the forces in the x, I have ax plus ex plus dcx, which we know is 0.8321 times dc equals 0. Sum of the forces in the y equal dcy, which is 0.5547 plus ey minus 80 equals 0. So 0.5547 dc plus ey equals 80. So here, this is another equation. So this is equation 4. Here's equation 5. I need 3 more equations. What page number am I up to? This is 6. This is 7, 8, 9, 10. Okay, I used this free body diagram. I used the whole structure free body diagram. I used BE free body diagram. So I'm left with this one. So now I'm going to do free body diagram A, B, C, F. Let's just draw it. A, 3 feet. B, another 3 feet. C, F. That's only 1 foot, right? We have 3 feet. From here to here is 3 feet. And from here to here is 1 foot. And we have AX. We have, remember, we have to make sure that we're drawing all the forces in the right directions. BY. BX, sorry, that's X. CD is going in this direction. And at F, we have FY and FX. And I just want to do a last check that if I drew D going here, then this one has to go in that direction. That has to go in that direction. Correct. All right. So we already found out what FX and FY were. We found out that FX is -80 and FY is -80. And that's the only ones we know. Okay. And we know that DC is, let's just write this over, 0.8321I plus 0.5547 J pounds. So let's do it. Sum of the forces in the X equal, because we need, how many more equations we need? We needed 10 equations, but we found 2. So now we need 8 equations. And we have 1, 2, 3, 4, 5. We need 3 equations from here. So AX minus BX plus DC times 0.8321 plus FX equals 0. So AX minus BX plus 0.8321 DC equals, well, FX is a negative, so it comes out to be 80. And this is my equation 6. Sum of the forces in the Y equal -BY plus FY plus 0.5547 DC equals 0. BY is down, FY is up. This is positive. Here's my equation 7. And let's figure out where we want to do our moments about. Let's just do the moments about A. All the forces that are in the X are going to go right through it. So it's going to be BY times 3. And it's negative. BX goes through it. CDY is 0.5547. And it's going up. So it's times 6. And it's positive. And then FY times 7. And it's positive equals 0. So -3BY plus 6 times 0.5547 equals 3.328 CD plus 7 times FY, and FY we know is -80 equals 0. So -3BY plus 3.328 CD is equal to -560. 8 times 7 is 56. And here's my equation 8. Okay, this has got to be the hugest problem we did so far. So that was page 10. Now, page 11. We are going to do a huge matrix. We have all these equations. So we're going to do an 8 by 8 matrix. Ready? Okay. So let's have enough space for 8. Okay. God, and then I have to have an 8 by 8 here too. I probably should have did it sideways. Okay, well, let's figure out which unknowns we have. We have EX, EY, we have AX, we have DC or CD, we have BX, we have BY, we have CX and CY. Remember that FX and FY aren't in it because we already have them. Equation 1 says BX is here. So let's just write the thing. EX, EY, AX, DC, BX, BY, CX, CY. So I'm putting the coefficient. So the first equation, this is the first equation. BX plus EX is equal to negative 80. So BX, BX plus EX is equal to negative 80. That's our first equation because equation 1 goes here. Equation 2, 3, 4, 5, 6, 7, 8. Okay. And then all this is 0, 0, 0, 0, 0, 0. Equation 2 was EY plus BY is equal to 0. 0, 0, 0, 0, 0, 0. Equation 3 was 3BY. 3BY plus 4BX 0, 0, 0, 0, 0, 0 is equal to negative 240. Okay, fourth equation, AX plus EX plus 0.8321 DX equals 0. Fifth equation, EY plus 0.5547 DC equal 80. That was page 9. Where's page 10? 8, 9. Oh no, here it is. Okay, page 10's equation. Equation 6 is AX minus BX, so minus 1, plus 0.8321 equals 80. Equation 7 was negative B1 plus F. Oh wait, FY. We have FY. So it's negative BY plus 0.5547 DC is equal to, what was FY? FY was a negative 80, so it equals 80. So this is really equation. So it's negative B1 plus 0.5547 is equal to 80. 0, 0, 0, 0, 0, 0. And the last one is negative 3BY, negative 3BY plus 3.328 0, 0, 0, 0, 0, 0 equals negative 560. So now we have an 8 by 8 matrix. We have an 8 by 1 matrix because the row goes first, and an 8 by 1 matrix. And now we punch it into the calculator and we find out what all these values turn out to be. And let me write them down because I already solved the problem. And they're all going to be pounds, right? You're working with pounds. Yep, pounds. 10, 11, and CX is 160. DX, they found it into different. CY is 107. BY is 26.7. BX is 80. EX is 0. EY is 26.7. AX is 160. And I just have the components of these to tell you right now. DCX and DCY. DCX, DCX is 160 and 107. And now let me just check the signs to make sure that I drew it the same way, the arrows the same way I drew it before. Look back at the free body diagrams. No, the B's have a negative in front. And that goes that way, great. FY we already found. And then EX and EY is okay. And B is negative. Hang on. I'm recording. Okay. So you guys, that was an extremely long problem. But that's how we do frames. So let me just take a pause for a moment. Hey, I just looked a little closer at the free body diagrams, and I think there was an easier way. If you look at the free body diagram for ABCF, if I did the sum of the moments about B, the two B's would cancel. The AX going through here would cancel, and I would have been able to find CD. So once I did the pulley, I found FX and FY. If I knew FX and FY, I could have done some of the moments about B, and I would have found CD. And then if I found CD, I could have done some of the forces in the Y, because I knew the Y component of CD, I could have found what BY was. So this free body diagram might have allowed me, it would have allowed me. So the pulley, I found FX and FY. If I did this, did some of the moments about B, I would have found CD. Then if I did some of the forces in the Y, I would have found BY rather. Then I could have went here and did some of the moments about E, because I have BY, and then I could have solved for BX. And then I could have done some of the forces in the X, some of the forces in the Y. Boy, I would have found them without doing a matrix. I'm hoping you're still watching the video. This free body diagram first would have given me FX and FY. This free body diagram, do some of the moments about B, I would have gotten CD. Some of the forces in the Y, I would have found BY. Some of the moments about E, I would have found BX. Some of the forces in the X would have found EX. Some of the forces in the Y would have found EY. And then the only thing I need is A. Then I come back to this free body diagram and I do the sum of the forces in the X and I find AX, or I do some of the forces here and find AX. So I did just show you way more complicated problem. I solved it way more complicated, but at least you got an idea of what it is. But now you're also seeing that there's often a way to figure out which free body diagram to use and which equation to use to find it without having to do matrices. So one last time, This free body diagram gave me fx and fy. This free body diagram doing some of the moments about B would have given me CD or DC. Then some of the forces in the Y would have given me BY. Then I go here, do some of the moments about E, I would have got BX, do some of the forces in the X, some of the forces in the Y would have given me the E's. The only thing I had left was the A. I could either use this free body diagram or this and do some of the forces in the X. Okay, I'm going to put it on pause again. Okay, so the last thing I want to do is just review the modules with you on frames. So I'm going to share my screen. And remember, there are 2 modules, what we covered last Thursday, which we did a review at the beginning of this class, and then this Tuesday today, which is lesson 2 of 2. Everything's the same in both. What I did is the first frame lesson has the overview, which we're going to go over a little bit. And then I had some pictures of erector sets, which you may have played with when you were a kid. And we have a bunch of this in the lab. But this is all dealing with frames and pin connections. Anyway, let's go back. So in the lesson 1 of 2, I have this, and then I also have the problems that we worked on. And I did post a lecture notes in the Zoom recording. And then in this one, I posted the problems again because we finished up the same problems. Here is the homework assignment, and I have some videos on the assignment as well. And then here is the quiz that you're taking today. But what I wanted to do is go back and just give you an overview. So by the end of the module on frames, you're going to learn the difference between 2-force, 3-force, and 4-force members. And it really is defined by how many points on the member that there are external forces or reactions. Okay. And then for 2-force members, you know the reactions at a pin at the end now isn't in the axial direction. So it reduces 4 unknowns to 1 unknown. So free body diagrams for analysis of frames, typically your first free body diagram is the one of the whole structure separated from the main supports. Second free body diagram is the member in question if they're asking you only to find some reactions on some members. And then a third free body diagram if you need more equations. And then there are times that you're going to have a problem where it says find all the reactions at the supports and the forces. And that's what that second question was all about. So we did the given and find, we made up a table, and then we started going through equations. And sometimes you're going to wind up having a bunch of equations and unknowns, and you could plug them into your calculator. But in situations where they're only asking you to find some unknowns on one member, typically, again, you're going to do given and find, you're going to do a table. The first free body diagram is usually of the whole structure. And then the second free body diagram is the free body diagram of that member. Okay, I'm going to stop sharing. Okay, so I will see you on Thursday. Thursday, we're going to start friction. Okay, thanks. Bye.